Okay, we are on how equilibria respond to temperature changes. And Le Chatelier's principle says that when we have a system at equilibrium, if we change the temperature, we're going to shift to remove some of the added kinetic energy, that's if we increase the temperature, or we will replace some of the removed kinetic energy, that's if we decreased the temperature, okay? And we have to take into account, are we dealing with endothermic or exothermic processes? So here, if I'm looking at this system and my delta H is positive, which means this is an endothermic process. That means that I have heat as a reactant, okay? If we heat this system, so I'm increasing the temperature, we are adding some kinetic energy. Anytime you increase the temperature for an endothermic process, since heat is a reactant, if I'm increasing it, I need to bring it down a little bit to help me get back to equilibrium. So I need to consume some of it. So I'm going to shift to the right to consume some of that added heat, if you want to think of it that way. That will bring down my kinetic energy and help me get back to equilibrium, which means the concentration of NO will increase and the concentration of N2 and O2 will decrease. Let's take a look at this next example. We're going to cool this system, so I'm going to remove heat, and there's going to be a decrease in kinetic energy. If my delta H is positive, this is an endothermic process. My heat is a reactant. If I remove heat, think of it as I am removing a reactant in an endothermic process, which I'm going to need to replace to help me get back to equilibrium. So if I shift left in the direction of heat and I produce some more to replace the heat that I removed, then I will get back to equilibrium. So that's why we shift left, which causes the NO to decrease and the N2 and the O2 to increase. Let's take a look here. The system below is heated. So I increase the temperature, which is increasing kinetic energy. Now, this time my delta H is negative, so this is an exothermic process. So that means that heat is a product. Heat is being released in exothermic reactions. So if I'm heating an exothermic reaction and heat is a product, I need to consume some of that added heat to help me get back to equilibrium. That means I'm going to shift to the left. And when I do that, the concentration of SO2 and O2 are going to increase, and the concentration of SO3 will decrease. For number 2, if I cool this system, so I am going to decrease the temperature, which means I'm going to decrease the kinetic energy. And this is a exothermic reaction because I have the delta H value in the equation on the product side, okay? So that means that heat is my product. So if I'm decreasing temperature, think of it as decreasing heat, decreasing a product. I need to bring some of that heat back so that I can get back to equilibrium, which means I'm going to shift in its direction. So I'm going to shift to the right. I think, yes, that's correct. And then the HI concentration is going to increase. and the H2 concentration and the I2 concentration are going to decrease. Let's talk about the effects of volume and temperature changes on the equilibrium position. So when the stress is a sudden concentration or volume change, you're going to see this as spikes on plots, which we've done so far, and I've pointed out to you, of concentrations versus time. Temperature changes don't appear on these plots, so the system responds to that invisible stress. And another difference is that concentration changes can be really, really sudden, but the temperature of a system can't change that rapidly. So that means that chemical systems begin responding while the temperature is still changing. So the response begins before the stress is even complete. And if we take a look at the next page, here you see that changes in concentration show up on a graph, but the temperature change actually doesn't. Let's talk about the shift mechanism. And the effect of temperature change on forward and reverse reaction rates, okay? So increases in temperature cause a shift in the endothermic direction because they increase the rate of the endothermic direction more than they increase the rate of the exothermic direction. The endothermic direction has a much harder time because of its activation energy, so it obviously benefits from an increase in temperature more so than if it was exothermic, okay? So in equilibrium's endothermic direction, so in this case, I'm moving here in this forward direction. This is an endothermic versus the reverse is exo. Do you see how large this activation energy is for the forward direction as opposed to the reverse direction, which is exothermic and has this much lower activation energy? Okay, so you'll see a much bigger, more dramatic change or sensitivity in the endothermic direction with a temperature change because of that activation energy. If you take a look here at this sample problem, it says explain in terms of forward and reverse reaction rates how the system below would respond to being heated. So this is an endothermic process. That means heat is a reactant. So what happens is you're going to end up shifting to the right to consume some of that extra heat. So that's going to increase the forward rate a lot more than the reverse rate would, okay? Because that's the endothermic direction. If you take a look down here at this sample problem, here we are cooling it. I didn't need to erase that. This is an endothermic process. Heat is a reactant. When you cool it, you're removing a reactant, you're removing some heat. So that means you would need to shift to the left to replace some of that heat. So when you cool this, you're going to see a decrease in the forward rate more than the reverse rate, which is why you're going to end up with this net reverse reaction, which is why you're shifting to the left. Let's take a look at some sample problems on the next page. Explain in terms of forward and reverse reaction rates how the system would respond to being heated. This is an exothermic reaction. Heat is a product. That's why I'm writing it in there. So if you heat it, you need to consume some of that heat that you added to help get you back to equilibrium, which means you're going to shift to the left. And that means that the reverse rate is going to increase more than the forward rate, which results in a net reverse reaction. Number 2, explain in terms of the forward and reverse reaction rates how the system below would respond to being cooled. Well, here you have heat as a reactant, so this is an endothermic process in the forward direction. So if you're cooling something, you're removing some heat. We need to replace some of that heat to get back to equilibrium, so you need to shift to the left. So when you shift to the left, the forward rate decreases more than the reverse rate, which results in a net reverse reaction. Number 3. Show how the forward and reverse reaction rates in the system below respond to a temperature increase at T1. Use a solid line for the forward rate and a dotted line for the reverse rate. The system restores equilibrium at T2. Okay, here's my reaction. This is exothermic, which means heat is a product. So if I'm increasing the temperature, I've got to consume some of that extra heat, which means that my, let's see, there's a temperature increase at T1. My solid line is my forward rate, and my dashed line is my reverse rate. So my reverse rate is going to be increasing, and then it will level off at T2. And then my forward has to come up to meet it. Since I'm shifting to the left, this is my initial equilibrium. Here is my reverse rate increasing much more than my forward rate, and then the forward rate and the reverse rate will be the same at my final equilibrium. Okay? Now, let's talk about the Haber-Bosch process. So almost all of the ammonia in the world is produced by this process. And 80% of the ammonia in the world is used to produce fertilizer. Fritz Haber developed the equipment and procedures for producing ammonia in 1910, and he received the Nobel Prize in 1918. In 1931, Carl Bosch won the Nobel Prize in Chemistry for putting this on an industrial scale. You should read the process, production rate, and temperature considerations for the Haber-Bosch process. To sum it up for you, lower temperatures actually produce a higher percent yield, but at a lower rate. And they use a catalyst to increase the rate at lower temperatures. And higher pressures generate faster rates and tend to push the reaction towards a higher percent yield, generally speaking. But you should read through this entire process about why lower temperatures produce higher percent yields of ammonia at equilibrium, because the lower temperatures actually shift the equilibrium towards the products, okay? In the quick check here, it says name the chemical produced by the Haber-Bosch process. That is ammonia, which is NH3. And what increases the rate of the Haber-Bosch process without decreasing its percent yield? That would be adding a catalyst.